Hey everyone, welcome. This is a session on dynamic memory. My name is Brian Sarasi. I'm a senior program manager on the Hyper-V team, part of the Windows division at Microsoft. I've been with Microsoft for about 10 years. I've been with the Hyper-V team pretty much since we started virtualization. Originally, we started with Virtual PC and Virtual Server, and then with Windows Server 2008, we came out with the Hyper-V technology, followed with R2, and now with Service Pack 1, which has added the dynamic memory feature, as well as the remote FX feature. So our agenda is to talk about memory and virtualization. Why are we doing dynamic memory? What are the goals behind dynamic memory? We're going to talk about various techniques for memory consolidation, both ones that we've used, ones that are also in other products out in the industry, why we chose what we chose, why we think it's a good option, why do we think it's the best choice. We'll talk about some of the concepts. We'll also do a demo of dynamic memory, so we'll take a look at it in action. We'll talk a little bit about the system impact that dynamic memory can have and some considerations when you're thinking about deploying dynamic memory. A little bit of housekeeping logistics. We do have microphones for questions. I will ask that we keep the questions to the very end. I will warn you though also, I do have a session immediately following this one on Hyper-V Cloud Fast Track. So if you're running a little long, I do apologize. We may need to cut the questions short, but I do encourage you to come to the booth, the TLC. I will be there later this afternoon, so if we don't answer any of your questions as part of this session, please feel free to come find me and ask any questions that you have at that time as well. Okay, so memory and virtualization. Why are we doing dynamic memory? What is the point? Well, what we've found, and this is by no means any criticism to anyone in the audience, but when we talk to a lot of our customers, they don't necessarily know what amount of memory they should be allocating to different workloads inside of virtual machines. So we ask these questions. How much memory does a server actually need? Your IIS servers in your environment, how much memory do they need? How much memory are you giving them? What about a print server? A file server? What about branch cache, direct access? And then the last question is an interesting one. What will the performance be if you cut the amount of memory in half? What would the performance be if you double the amount of memory that you're giving to any particular workload? Usually people that are running their environments don't necessarily know. They might have a general guess or a good feeling for a certain number of workloads, but they don't know every single workload that's been created. They don't understand all the different line of business applications, and they don't have good insight into exactly how much memory is needed for each workload and how those workloads will behave if you give them more or less memory. These are some quotes that we've heard from various customers. The first one, new virtual machines get 1 gigabyte of RAM no matter what the virtual machine is running. I only give more memory if the application owner complains about performance. So that's an interesting model. They say, I don't look at the system specs, I don't talk to the application developers, I just give them 1 gigabyte of RAM. Once they start complaining, once they start saying that my workload isn't working properly, or is slow, or is sluggish, then they start allocating more memory. But there's fundamental flaw there. One can be, not all application owners, not all application users might actually communicate back to you that they're having issues. There are people out there that will suffer through bad performance. Their workloads are really getting starved from memory, but they don't communicate it back to you. They just kind of deal with the frustration. Another quote that we see is all virtual machines get 4 gigabytes of RAM. This is a little more rare, but their attitude is, I'm going to give it plenty of RAM for most workloads. I don't have a clue if it's really using that amount of memory. Maybe it's only using 1 gig, maybe it's only using 2. But when I deploy new workloads, I give it 4 by default. Typically, people don't complain, so it just works. It's another philosophy, but obviously the downfall of that one could be that you're over-allocating RAM. There are plenty of workloads that for 90% or for 100% of their given life cycle, they'll never hit 4 gigabytes of RAM. So though that option may be sufficient for your users, you could be inefficiently using your memory resources. The third quote that we see is, I look at the system requirements. Some people say if the system requirements say give it 4 gig, I give it only 50%. Those are more of the skeptical people believing that application developers who write the system specs estimate high. So their attitude is, if it says 4, I'm going to give it 2. Some people give it 1 to 1. If it says 4, I'm going to give it 4. Other people says, if it says 4, I'm going to give it 8. I'm going to double it. So they look at the system specs, and we see different people kind of making decisions based on that. And then the last one is a vendor. So that's a vendor tells me their app needs 4 gigabytes of RAM. I do not have time to test this is true or not. Again, this goes to the same philosophy as I'm skeptical. I don't necessarily think that their application really needs all that amount of memory, but I don't have the time, I don't have the resources to really evaluate whether or not I need that amount of resource. So when you're thinking about memory, it really is a key factor when it comes to consolidation. We all understand virtualization. We all understand the benefits. We're taking these old, systems, old physical computers that are running a single workload. Most of the time, they're underutilized. We're consolidating these workloads on fewer instances of hardware. This is all good. However, 9 times out of 10, the first resource that you run out of is going to be memory. Historically, before Service Pack 1 with Hyper-V, we obviously did processor overcommit. Originally, we did 8-to-1 overcommit. Now we do 12-to-1 with Service Pack 1. So basically, you can run 12 virtual machines to 1 physical core. We do disk overcommit, essentially. What I mean by that is that we allow multiple virtual hard disks to reside on 1 physical disk. Obviously, we do networking overcommit to the point where you can run multiple virtual network cards over 1 physical network card. But historically, memory is the one thing that we don't share. When you gave it 1 gigabyte of memory, regardless of how much memory the system really needed, it would take 1 gigabyte on the host. So typically, again, when you're looking at your workloads and when you start looking at consolidation, the first thing that you run out of memory. Memory is expensive. Systems have limits on memory. If we can basically share the memory, actively use resources to kind of dynamically give and take memory based on the resource needs of the virtual machines, your consolidation numbers can go up significantly. So the customer requirements, when we were looking at the various different options of memory techniques and where we're going to do, we focused on these requirements. The first being maximum density without sacrificing performance. There are methods that are actually very high CPU intensive. They're doing a lot of hashing, they're doing a lot of calculation trying to determine how to consolidate. We don't want to sacrifice memory consolidation, memory density, for a lot of high CPU cycles. So we want high density, but we don't want to see the other resources in your system get pegged. Another customer requirement, maintain consistent performance. What we don't want to see, as memory is given and taken from virtual machines, we don't want to see dramatic performance spikes and valleys. We want it to be dynamic, we want it to be fast. When a virtual machine needs memory, we want to make sure we give it to it quickly. When it doesn't need memory and another system does, we want to take it and allocate it somewhere else quickly. We don't want this to be a long process. We don't want a virtual machine to say, I need memory, 5 minutes later it gets it. It needs to be quick, it needs to provide maximum and consistent performance to the running virtual machines. And then lastly, it obviously needs to be suitable for production use. There are a lot of memory techniques that are great for dev and test, where you're giving a lot more memory than the physical system really has. That is okay if you want to test your application with large amount of memory, but from a performance perspective, it's going to be very poor. So we want to make sure with any technique that we implement that the performance stays high, that this is good for production environments as well as dev and test. So now we're going to take a look at some of the different techniques out there for memory optimization and memory consolidation. The first is called ballooning. And essentially what ballooning is there is an application driver that's running inside of the virtual machine. In some regards, you can consider it a hungry application. And essentially what it does is when the system needs memory, it will balloon up and it will tell the operating system inside the virtual machine that I need memory. The operating system basically tries to grab memory, gives it to that balloon driver. That balloon driver then in turn gives it back to the host. And now the host can essentially use that amount of memory that it just took from the virtual machine and give it to another area. So that's the balloon driver blowing up. Conversely, when that virtual machine needs more memory, that balloon driver shrinks. The host can essentially give memory back into the virtual machine. Another option is what we call page sharing. Page sharing is an interesting one. So essentially, let's say, for example, I have 10 virtual machines and they're all running Windows 7. It can be expected that there are multiple identical pages amongst all those Windows 7 operating systems. There are just certain things in memory that are consistent for every Windows 7 instance. So the concept here is, why don't we go ahead and remove all of those duplications and consolidate that one single page. Instead of 10, we'll bring it down to 1. So this is an interesting concept. A lot of people right off the bat say, security, we're now sharing memory across virtual machines. In some regard, that's true, but there are very good and very reliable methods of doing page sharing, where you're doing a bit-by-bit comparison. You're ensuring that these two pages from these virtual machines are in fact identical, and you're still retaining that isolation of the virtual machines. But the fundamental problems with page sharing is, number one, it's not dynamic. It takes a significant amount of time for the host operating system to basically determine that these pages are identical. We can't just do a surface level scan. We actually have to do a bit-by-bit analysis and make sure, with no uncertainty, that these pages are identical. Only then can you actually consolidate them. So number one, this can actually take a large amount of time. If these are large pages, if this is a lot of memory, it could take minutes. In some cases, it can take hours. Well, we just lost our dynamic ability. Maybe over the long haul, I'm starting to give resources back to the host, but it's not that dynamic give and take. It's not that dynamic ability to respond to active workloads and their need for more memory. And one of the largest benefits is zero pages. Operating systems will have 0 pages. The host is working on those. The host is calculating those. The host is identifying those. And essentially, you're consolidating 0 pages, and you're giving no new net gain when it comes to memory. And also, with some of these jumbo frames and these large packets, these large frame sizes, or these large memory packet sizes, a lot of these page sharing techniques don't work with these large packets as well. And the last one that's not in here, this can be very CPU intensive as well. If we remember, one of our goals was to make sure that we don't peg the processor, that we don't use other system resources in the goal of basically giving back memory. And page sharing can be very CPU intensive, as it's constantly analyzing which pages are identical and trying to consolidate. Page sharing is not a method that we chose to implement. Second level paging. So second level paging basically, so we all understand the concept of paging. This has been happening in Windows and all operating systems since the very beginning. The general concept of paging, or paging to disk, is when you're out of memory and an application needs it, you'll actually write those memory files to disk instead of keeping them in memory. Now what happens is there's basically host-side paging and there's guest-side paging. And in any implementation, whether it be Hyper-V or VMware or others, there is paging that can happen. If all the virtual machines are trying to get all the maximum amount of memory that they can possibly be allocated at the same time, it is possible that the virtual machine or the host will essentially run out of memory. So what happens? Now, typically what we try to prescribe is using dynamic memory along with live migration. So you'll actually identify using Operations Manager and Virtual Machine Manager that your host is out of memory, and you can live migrate those virtual machines onto a host that does have memory. But let's assume for a second, for the sake of argument, that we don't have live migration. What will happen? Those memory pages pages will actually be written down to disk. We will do paging. Now, there are two different ways of doing it. You can do host-side paging. So the host basically says, I'm out of memory. This page from the virtual machine, I can't put into memory. I'm going to write to disk. And then there's guest-side paging. This is where inside of the virtual machine, it says, I don't have any more memory. The host won't give me any more memory. I'm going to write my pages to disk. And there's a big difference between these two methods. On host-side paging, we have no insight into what memory pages we're actually paging. We could be paging system files, we could be paging random zero files, we don't really know. So there's a big issue there. The host is basically treating the virtual machine as a black box. It doesn't understand what's inside of it, so it's just randomly grabbing memory pages and putting them to disk. You don't want to page system files. If you let the paging happen inside the virtual machine, the operating system in that virtual machine will not allow its system files to be paged. It will page other non-important files first. So in the case of Hyper-V, in the instance that we run out of memory, we allow the virtual machine, in this case the Windows operating system in the VM, to do paging itself. Now again, we try to avoid paging at all costs. It's not a good thing to do, but if it has to happen, let the virtual machine, let the guest operating system decide which pages to page. By doing it on the host, they could make bad decisions. It can page a system file, and then what happens? Inside of the virtual machine, it can try to launch another system file to make up for the difference, and you start kind of getting in this vicious circle. This is just another example here, a little more depth into why paging in general is bad and why we try to avoid it. As everyone knows, memory is fast, disk is slow. This is just a numeric representation of that fact. Here you can see different memory speeds, DDR3 1600, all the way down to DDR3 800, in the range of 10 nanoseconds to 5 nanoseconds seek time. Compare that to a traditional disk, we'll say approximately in the range of 8 milliseconds. If you do the math, here's some examples at the bottom. DDR3 1600 memory is approximately 1.6 million times faster than disk. Paging is not a good option. And this is kind of coming back to one of our key principles for dynamic memory. Make sure it works in a production environment. In production environments, you don't want significant degradation. You want to avoid that at all costs. We try to avoid paging at all costs. There are other techniques. Some of these we are investigating still. One is guest-directed page sharing. So this is still the host is doing the paging, but it's actually communicating into the guest. And so together, they're kind of deciding what pages should be put into disk if necessary. We're also looking at memory compression techniques. These are kind of things on the future. We're not currently implementing these. Most other virtualization platforms are also not currently implementing these, but these are, provide some possible areas for further improvement down the road that we're looking at. So let's take a look at dynamic memory, specifically what we chose to do. So obviously our goals, higher VM consolidation ratio with minimal impact. This is interesting though. People oftentimes ask, okay, great, I'm going to deploy Service Pack 1. I'm going to implement dynamic memory. How much memory am I going to save? How much more consolidation can I get? And unfortunately, that answer isn't easy. It really depends on a couple of factors. Number one, it depends on how much variation your workloads have. Some workloads have a lot of variation throughout a given day, maybe even throughout a given hour, or maybe throughout a given minute. Sometimes the memory spikes, sometimes it goes down. One case of this oftentimes is VDI workloads, or virtual desktop. Now in the case of dynamic memory, we wanted to make sure that this feature works both for server workloads and VDI workloads. But oftentimes in VDI workloads, we see a user, they're going ahead, they're watching a video online, they're running a PowerPoint deck, they have Excel running, maybe they're running AutoCAD, who knows, they're doing a lot of different workloads, and the memory is very high. Then they go off to lunch, and for that next hour, the memory plummets. In that case where you have these dynamic fluxes of memory utilization, consolidation can drastically improve because at those times of low, we can actually consolidate, take back that memory, and hence run more virtual machines. On the other hand, there are server workloads, for example, not all, but some server workloads that are very consistent. There are some SQL workloads that regardless of the day, regardless of the time, they're just taking the same amount of memory, they're real consistent, they're just a workhorse. In that case, you might not see a lot of memory consolidation happening because you're not giving back memory, you're not taking memory. SQL is just running straight. Again, not all SQL workloads, but there are ones that have that attribute or that trait. And then the second bullet point here is also critical. How good were you initially when you allocated memory? Again, this gets back to those different personas that we were looking at earlier. Some people say, I take the system requirements and I double it. If you're one of those individuals, dynamic memory is likely going to have a big impact. You're probably giving all your virtual machines today too much memory, so when dynamic memory comes in, it's going to do a good job of consolidating that. However, if you're on the other spectrum, where you're one of those people that say, I only give my virtual machines 1 gig, or I take the system requirements and I cut it in half, and I don't increase memory until the user complains, then you might not see a lot of improvement with dynamic memory. You might already be actually starving your virtual machines, and when you turn on dynamic memory, the system might automatically decide these virtual machines, these workloads need more memory. So you actually might, in some rare cases, see memory go up. You're actually consuming more memory than you were prior. But the beauty of dynamic memory is the system is figuring it out. It takes the guesswork out of the equation. You don't need to run long, laborious tests to determine memory utilization. The system is dynamically monitoring and dynamically giving memory and taking memory from the virtual machine as needed. And again, as I mentioned, one of our key goals is this must work well for both server and client workloads. And also, as I already mentioned, we must add minimal overhead to the system. We don't want to use techniques that are high CPU intensive. And then also, this one is a little more vague. This last one on the list here is a little confusing for a lot of our test team to kind of get their head around. It's kind of nebulous, it's not very actionable, but it's this must pass the that looks right test. And what we mean by that is when you're looking at the memory utilization, when you're looking at the memory statistics in Resource Manager, we don't want them to be completely off the wall. We don't want them to be odd. We want to be able, when you're looking at the right counters, to be able to understand what's happening, make logical decisions. We don't want the memory counters just to be completely off the wall. Now, as I will talk about a little bit later, the method that we did choose actually screws up the memory counters a bit inside of the virtual machine. But we have articles and we have guidance on what counters to look at, what statistics to look at when you're determining really how much memory is being used. So, understanding philosophical differences. When we first started taking a look at dynamic memory, or actually before we called it dynamic memory, when we were looking at memory techniques, we tried many different memory techniques. We had different lab environments. We had different prototypes that we set up. We, of course, were looking at what other vendors, including VMware, was doing as well. And we started seeing some differences, and we started trying to understand why is some companies, whether it be Xen or VMware, doing it in one way, and why are we going down a path? Why is all our prototypes and all of our research pushing us down a separate path? Now, our first thought, or at least my first thought, was, hey, we thought of something that VMware hasn't thought of. This is good. We're doing it different. We got a great technology here. And then, of course, late at night, when you're all alone, you start thinking, oh my gosh, maybe VMware's thought of something that we haven't done. That we haven't thought of. What are they doing that's so good that we haven't? So we started doing more research and trying to understand why is our technique divergent from VMware, what's good about their options, what's good about our option. And what we came down to is there is a philosophical difference around how to treat a virtual machine when deciding memory consolidation and memory techniques. VMware, for example, and this is a very valid option to choose. I'm not saying that this is necessarily wrong, but they treat the virtual machine when it comes to memory as a black box. They don't look inside it. They're not paying attention. Is this running Windows? Is this running Linux? They're not trying to understand what the virtual machine is doing, what its memory utilization is inside the VM. They treat it truly as a black box. Now, that has some advantages. It's reliable. It's always consistent. But we at Microsoft, we know one operating system really, really, really well, Windows. Number one virtualized operating system on any virtualization platform is Windows. In fact, the Hyper-V team is part of Windows Core Kernel. The guys who run Windows Memory Manager for the Windows Server operating system are literally down the hall from the Hyper-V team. Our attitude was different. Our attitude is, let's look inside the virtual machine, let's work with the virtual machine and the operating system inside that virtual machine, and let the host and the virtual machine together make decisions based on what's happening as to what memory consolidation and what memory give back and take should be happening. So these are fundamental philosophical differences, and we chose to basically enlighten the host and let that communicate with the virtual machine. VMware, for example, tends to treat the virtual machine as a black box and make the decisions on the hosts exclusively. So from our perspective, dynamic memory, some of the benefits is obviously it enables higher consolidation ratios per host by addressing the greatest limiting factor, memory. This is a production feature, and essentially how it works is memory is pooled dynamically and securely distributed across the virtual machines. Memory is dynamically added and removed. This little bar graphical depiction down here is simply showing that memory needs to go up when it goes up and memory goes down when it needs to go down. There was some misinformation out there saying we're using hot add memory, and therefore to give back memory, the virtual machine must be turned off. That, in fact, is not the case. Memory dynamically gets added and removed from the virtual machine. So how does that happen? Adding memory is done in an enlightened fashion. And if you're not familiar with that term, that's a term we use commonly. We call it enlightenments or synthetic device drivers. So this is a concept that we've had since the first version of Hyper-V. This is basically the host side and the guest side communication. We call them integration components or integration services or enlightenments. All of these things are used synonymously. This is basically communication that's happening between the guest and the host over what we call VM bus, which is our high-speed in-memory bus for guest-to-host communication. Integration components do simple things like mouse integration to make sure that the mouse works properly inside the virtual machine, host time synchronization, so the virtual machine can actually pick up the time from the host. We also bring in our enlightened drivers like our synthetic network card driver. In the case of RemoteFX, if you're familiar with that technology, also in Service Pack 1, we use our synthetic device driver model to basically insert a graphics card into the virtual machine that's on the host server for high-end graphics performance. Now we have the concept of another pairing, another integration component. We call it VSPs and VSCs. This is the virtualization service provider and the virtualization service client. One sits on the host, one sits on the guest. And this is the communication between the host and the guest when making decisions around dynamic memory. So we add memory using this VSP or VSC pair, and essentially we're doing it from the host to the guest over this communications path. Now, removing memory, we did do the ballooning effect. So we have a balloon driver. This is also included as part of the service integration components. So the balloon driver, when the virtual machine doesn't need the memory and the host wants it, the balloon driver will grow and give the memory back. And again, then we use the enlightened drivers to essentially add memory back into the virtual machine when necessary. So our add, remove are using these two technologies combined as a pair. System requirements, because we are communicating into the guest, we do have limitations on specifically what virtual machines can be used with dynamic memory. But starting from the parent, obviously you need Windows Server 2000 and R2 Service Pack 1. You should be aware, but if you're not, Service Pack 1 is released. We're not in beta, we're not in RC anymore. It is RTM, it is a free download that you can get from Windows Update. I will talk about at the end of the session just some general guidance on how to actually upgrade to Service Pack 1 for dynamic memory. We also support this on Microsoft Hyper-V Server. For those not familiar, Microsoft Hyper-V Server is our free virtualization platform. It's essentially the minimalistic version and driver base of Windows with the Hyper-V role. There is no GUI, it's command line only, but it is a free option, and Service Pack 1 and dynamic memory has been enabled for that product as well. Guest requirements, this is a list of the operating systems that will take advantage of dynamic memory. Obviously, the latest versions of Windows, Windows Server 2008, 2008 R2, it's not listed there, but obviously 2008 R2 Service Pack 1. This has also worked for Windows Server 2003, both the 32-bit, 64-bit edition of those operating systems, and Windows Vista and Windows 7 is also supported, both 32-bit and 64-bit, but only the Enterprise and Ultimate editions. Those are the only client operating systems that are supported with dynamic memory. Now people ask, what if I'm running a Linux operating system or a Windows operating system that's not listed here? What happens if I enable dynamic memory? It just essentially won't be used. The base setting that you give, and we'll look at the settings for dynamic memory, the base setting or the startup setting that you give is what will be used, and that virtual machine will just consistently use that memory. We'll go through this quickly here because we actually do have a demo and we'll take a look at it a little more in depth. But this is just a screenshot of the UI in Hyper-V Manager for setting dynamic memory. In the old days, if you haven't seen Service Pack 1 but are familiar, the only thing we used to have was basically RAM. Now we have the option, you can still, if you want to, go static RAM. And if you say, for example, 4 gigs of RAM, it'll just give it 4 gigs. It will never take it. It will never add more. You can have static memory virtual machines and dynamic memory virtual machines on the same host. There's no problem with that. You can mix and match. But if you do choose dynamic, you'll basically have startup RAM and maximum RAM. I'll go into these more in depth a little bit later, but startup RAM is exactly that. This is what we're going to start the virtual machine up with. And the maximum is what will allow it to grow to. The default is always 512 and 64 gig. Many systems won't have 64 gig, that's okay. You can still set it at 64 gig, and that essentially is saying the maximum amount of system RAM that you have in your physical host. So adding and removing memory, people oftentimes want to understand how often does this happen? Is it happening instantaneously? Is it happening slowly? Is it happening quickly? Again, for a production workload, our goal was to make sure that if a virtual machine needs memory immediately and there is available memory, that it happens immediately. So when a virtual machine basically says, I'm running low on memory, it will be flagged and you'll actually see it in the Hyper-V Manager console. We will automatically, if the system has the memory available, it will instantaneously give that memory into the virtual machine, and you'll see the allocated memory go up. If the system does not have memory, it basically goes out and pings all the other virtual machines and says, which ones of you can give me memory back? And then those virtual machines that can relinquish memory, and then the host gives it to the virtual machine that needs it. This happens very dynamically. We do implement passive memory reclamation, though. So what happens, for example, is I start at 512 megabytes for a virtual machine, a workload spikes, and it goes up to 2 gigabytes of memory. Now, after the workload spikes and it's already been given 2 gigabytes of memory, let's assume it goes back down to 512 again. Does that memory automatically be given back to the host? And the answer is not necessarily. If no other virtual machines need that memory, if no other requests are coming into the host will just let it stay at that high 2 gig. The concept here is, since that virtual machine just needed it and just used it, there's a chance that it will need it again. So unless another virtual machine wants it, and I don't have enough resources to basically accommodate both, I'll let that virtual machine stay at that high memory. I'll only take it back when necessary. And then if it still stays idle after 5 minutes, it will be reclaimed as well. Startup and max, I covered this briefly already. So again, startup number of memory, our default is 512. The BIOS does not know about dynamic memory. This is kind of a funny anecdotal story, but when we were looking at very different memory techniques, when we were trying our different prototypes, one option that we actually looked at and built a prototype was creating an emulated BIOS or an emulated motherboard that had, I think we're up over 4,000 memory slots. Again, it was just an emulated motherboard. There's no physical motherboard in existence that large that I'm aware of. But our concept was, we'll create a big motherboard, the BIOS will see all these memory slots, and we'll use hot out of memory that's built into Windows to add the memory. And we started going down that path. We ran into a number of issues right off the bat. One is the hot add memory team, who, if you're not familiar with hot add memory, it was originally designed, and it's in the higher versions of Windows, but it was really originally designed for large scale systems. And the concept was that I actually have a running server, and if that server, this is before the days of virtualization, if that server ran out of memory, I could actually open up the case, and I can drop in a DIMM, plug it in, snap it in, and the BIOS and the Windows operating system will automatically basically understand it, consume it, and start using it. One of our techniques that we looked at in prototype form was actually using that method. And so we emulated this huge motherboard, and all of a sudden we started dropping in memory DIMMs synthetically and then removing them and going back. We just ran into all kinds of issues. We went over to the dynamic memory, hot add memory team, and their mind just started spinning because they were kind of thinking originally when they designed the technology, this may happen once in a while. Once a year, you might actually run out of memory on your system and need to drop in a DIMM. But we were doing it 100 times a second. We were pulling in memory, taking out memory, and it just basically fell the system over. So obviously, that wasn't the technique we chose to use. The BIOS is not aware of dynamic memory. We're doing this again all synthetically using our balloon driver and using our integration components, the VSPs and the VSCs. And again, the maximum, this is essentially saying don't let the virtual machine go above this amount. Again, our default is 64 gig. If your system has less than 64 gig, you can still set it that high. It will just go to the system maximum. We also have two settings, memory buffer and memory priority. The memory buffer is essentially saying how much additional memory should I try to allocate to the virtual machine above what the virtual machine is requesting. So most people, whether physical or virtual, try to run their workloads not right at the brink of maximum capacity. Usually you want a little bit of buffer, and our default here is 20%. So let's say that the virtual machine is requesting 1 gig of memory. Assuming you leave that buffer setting at the default, which is 20%, we'll try to add an additional 20% to that 1 gigabyte that the virtual machine is requesting, just to give it a little bit of room. Now you can set this lower, you can set this higher, but again, the concept here is most people don't want to have their virtual machine running just at the utmost maximum of allocation. You want to give it a little bit of buffer, and that's the setting. It's a slider, and we'll see it in just a minute. The other option is priority. This concept's been around since the beginning in Hyper-V. We have the concept of CPU priority in Hyper-V. And again, the concept here is if there is ever a contention, for example, in the CPU realm, if there are ever two virtual machines in contention for the same processor resource, the one with the higher priority setting will get the resource first. It's just literally, I believe the setting is between 1 and 10,000. It is. And our default is obviously right in the middle. But we have the same concept now with dynamic memory. If ever two virtual machines are in contention for same memory resources, the host will give that amount of memory to the virtual machine with the higher priority. Obviously, in the slider and the UI, it's not so granular that you can go from 1 to 10,000, but through the API, you can essentially set that, or through scripts as well. So let's go ahead and switch over. Enough talk. Let's take a look at, oops. Oh no, I dropped my clicker battery fell out. Let me just put this back together really quick. And while I do that, let me get these virtual machines starting. Okay. Destroyed my little clicker here. Okay, so here we have a Windows Server 2008 R2 Service Pack 1. This is obviously running the RTM bits. When we look at Resource Manager, and we'll just go into the general Resource Manager here, you can see that this is actually a 2-processor, 4-core each, so we have 8 logical processor system, and we have a total of 12 gigabytes of RAM in this host. Right now, we can see in Hyper-V Manager that we have a whole bunch of virtual machines. Most of them are currently off. Some of them here, these 5 are coming online right now. Here is the Memory Manager, Resource Manager for the host. And you again can see that right now we have a total of 12 gigabytes of RAM. And since what we're doing is we're running 5 virtual machines, They're coming up online right now. But what I want to do is go inside of them. As you can see by their name designation, these are the traditional static memory virtual machines. So if I go into the settings of one of these virtual machines, you'll see basically that we've set this virtual machine. This is a Windows 7, what we're calling a VDI client. So this is kind of our demo here is showing VDI workloads. But this is a Windows 7 64-bit virtual machine. And oftentimes when people are doing VDI workloads, 2 gigabytes of RAM is a common number. Some people like to go a little bit less, some people like to go a little bit more. In this scenario, this is looking at the traditional model before Service Pack 1. We've allocated all 5 of these virtual machines with 2 gigabytes of static memory. So if we go down into memory, and the virtual machines are still coming up right now, so our system's responding a little slowly. We can see here that the static button is checked and the memory is set at 2 gigabytes. Why is this great? It's great because the virtual machines are running. We only let you make changes to the dynamic or static memory settings while the virtual machine is off. However, down here we can see our memory weight and our memory buffer. If dynamic memory was enabled, these settings, both the memory weight and the memory buffer, can be adjusted, can be modified while the virtual machine is running. So here we can see, again, we have our 5 virtual machines all running 2 gigabytes of memory. If I go into one of them, what I've done is I've actually created a little script. It'll take just a second for it to come up. I've created a little script. It's just a little PowerShell script that randomly starts and stops applications. I have several Word documents, a couple PowerPoint documents, Excel documents, I have a web page, and I have a few PDF docs. And basically I set this PowerShell script. This is just trying to kind of come up with a generic workload utilization. So it's using every 30 seconds, it's randomly, well actually between 1 and 30 seconds, it's randomly starting an application, opening up documents, and again, every between 1 and 30 seconds, it then shuts down that document or web page or whatever it is. As it's coming up, you can actually see it down here in the little window. That's actually the PDF document. Here it is coming up inside of the virtual machine. So here again, you can see we just have virtual machines randomly opening and closing documents. This again, so here it's just opened up Adobe Acrobat. Now it's opening up some Word documents. What's interesting though is that I lost my mouse support. It's not the interesting part. It's odd. It's opening up also some paint or some desktop background images. Go back to the slide deck. Let's go back here, see if I got mouse back. Where did my mouse go? Sorry, I know where my mouse went. I'm on the wrong machine. I was on the... My fault. I'm like, what's happening with my demo? So that over here is the PowerPoint machine. This over here is my virtualization host. So completely my fault, my apology. Okay, so we're up over here. You can see now we've opened up some Word or some Excel documents. Now the point I want to make is obviously in the static memory virtual machines, we've allocated 2 gigabytes of RAM. It's not paying attention of how much RAM is being used inside the virtual machine. It's giving it 2 gigabytes. Now I'm just opening up different docs. Here you can see it's opened up a web page. These virtual machines aren't actually online, so this is actually opening up a web page off of the hard drive. But my point is, if we go into this virtual machine and we take a look, now we're looking at the resource monitor inside the VM, we can see that really we're only using right now 530 megabytes. We just opened up PowerPoint, so it jumped up to about 590. This virtual machine with these opening and closing applications will get upwards of a range of about 1.2 gig. But the point is, we're drastically underutilizing the resources that have been given to us. Obviously, this is a good scenario for dynamic memory. So we're going to go ahead and turn off this, disconnect this virtual machine For the sake of time, we'll just go ahead and hard turn off all these virtual machines. And up here, you can see we have a number of virtual machines. Obviously, if we look at the resource monitor on the host, we just turn off all these virtual machines. We have a lot of available memory. We have 11 gigs of available memory now for us. And the first thing I'm going to do is start up the same 5 virtual machines. So this is the same clone image that we're using before. It's the same PowerShell script that runs randomly, opens and closes applications. I'm going to go ahead and start these 5 virtual machines. The reason why I want to start them from scratch is to show you one thing. Here, we have assigned memory. This is how much memory that the host is given each virtual machine. Now, the default starting amount that I've given is 512, and allowed them again to go up to the maximum, which is 64 gig. I only have 12 gig in this host, so that essentially sets the maximum of 12 gig. But right off the bat, you can see it's only using 512 because Windows actually hasn't booted yet. Once Windows boots, and those integration components start communicating with the host, as they just started to do, you'll see the memory demand. The memory demand is, again, that communication between memory, host, and guest. And what I wanted to show you is what you're seeing here, memory status. It says low, it says warning. What it's depicting, or what it's picking up, is that applications are running inside of the virtual machine are requesting more than the 512 megs that we originally allocated. So that warning gets popped, that low reading happens, and then what you'll see is dynamically the memory is increased. All these virtual machines started with 512 meg of RAM. Now we got 600 meg, this one's got 776, this one's up to 8 megabyte of RAM, or 800 megabyte of RAM, and again, we're just dynamically adding the amount of memory that's needed for the system. So seeing this low setting is okay, but the low should go away quite rapidly once the host gives that virtual machine the memory that it's requesting. If we go into one of these virtual machines again, we can see here's my PowerShell script. Currently, it's no application is running. It again can have a pause between 1 and 30 seconds between applications launching and starting. Oh, it just opened up something. What did it open up? It opened up a couple different PDFs. And again, right here, you can see memory demand is going up, and the memory assigned memory is going up as well. So now, let's take a look at the host memory. Same 5 virtual machines running the same types of workloads, allowing the memory to go between 512 megabytes of RAM up to the limit of the physical host. Originally, when we did that, we were running full utilization on the host. We were running less than 1 gigabyte of available memory. Now we have in use about 5 gigabytes. Free, we have about 6 gigabytes of memory. Same workloads, less memory being utilized based on the workloads inside. Now, is this an exact science? Of course not. This is really dependent on the workloads that you're running. In this case, originally we're allocating 2 gigs of RAM. Our virtual machines are running less. We're almost pushing over the 1 gig limit. Once they run for a little longer, they will get over the 1 gig limit. But really, they're using less than half the amount of memory than we originally allocated, hence the reason why we're only using half the amount of memory on the host. But again, the key beauty here is let the host figure it out. Let the host dynamically determine the amount of memory that your virtual machines need and let it take care of that. Here we can see we finally saw one virtual machine, number 4, go over this 1 gig of RAM. So let's go ahead and push this even farther. We have our 5 virtual machines. Let's take it up to 10. These are the same workloads again, basically clone images. These were already running. They were in a saved state. This will take a minute or so for them to come out of a saved state. They're picking up the amount of assigned memory that they had when I basically put them into a saved state. So these have been running my script for a while. So several of them have gone over the 1 gig limit, or the 1 gig kind of threshold. But I also want to show you one thing why those are coming up. Let's go into one of these settings. So this is VDI number 5. We're going to go ahead and go into the settings. We'll go over to the memory. Again, 512. As I mentioned, these settings are grayed out, but the memory buffer and the memory weight is not grayed out. So let's see if we can see all of this on the same page at the same time. What I want to show you is right now, it's always trying to give it 20% extra buffer. So what that's saying is the memory demand of the virtual machine right now is approximately 700 megabytes. So what it's always going to try to do is give it 700 megabytes plus the additional 20%. So just for fun, let's go ahead and change this. We're actually going to increase this quite a lot, up to 200%. So what we're saying is right now we kind of have to look at the memory demand. Right now it's 700 meg. By doing 200%, we're saying let's add, not just double it, but actually let's triple the amount of memory on top of it. So now if we go ahead and apply the setting, it's up to 800 gig, or excuse me, 800 meg. We should see this essentially triple. Let me go over to apply. It's just over there. It's 800. I wonder if it's getting, should jump up. And there it goes, up to 2.5 meg, or 2.5 gig, excuse me, which is essentially the 800 times 3. So right there, dynamically, we basically said this is a priority virtual machine. I want to give it a lot of buffer. I want to give it a lot of extra memory. 200% is kind of an extreme, but it just shows that right there, dynamically, we've upped this up to the 2.5 gig, which is essentially tripling or adding 200% the necessary or required memory. Virtual machine is continuing to run. Let's go back into the settings. And we'll go ahead and dump it back down to 20%. So now let's take a look at what we have. Instead of 5 virtual machines, we actually have 10 virtual machines all running dynamic memory. Let's take a look at the memory on the host. We're pretty much right at our threshold now. We have 2 megabytes free. We can see that the memory is essentially being pegged. But again, we can add even more virtual machines. I'll go ahead and add 11 and 12. And we'll go ahead and do start. And what you'll see again is we're going to go ahead and add these, the amount of memory that was allocated when I save state the virtual machines. And what you'll see is in the assigned memory, the host now is saying I have more workloads coming online, I have less available resources. That assigned memory should start being shrunk by all the virtual machines just to make sure that they can properly allocate across the board. You will see more warnings, you will see more lows, because really we're starting to push beyond the amount that should be consolidated in this virtual machine. But as you can see, we're still relatively performant. Our virtual machines here in our Windows, you can see, is still running PowerPoint, our different applications. It's just at times, as you pack on more, you'll see some low settings because they'll be wanting more memory than is basically available at that given time. So that's just a quick demo of kind of what's happening with dynamic memory. Again, the key here is the host is making this determination. The host is deciding what needs to be done. Now, if I want to, just for one little more option here, let's go back into one of these virtual machines. Let's go ahead and say this one is the most critical. I care a lot about this virtual machine. Let's go ahead and give this again. Let's go ahead and double the amount of memory, so we'll give it 100% memory buffer. We'll go ahead and set priority high. All the other virtual machines set priority is to regular, so this one will be pushed above and beyond. And now we can go ahead and see we should get up to about the double amount of the memory demand. Right now we're about 1.5 gigs, so we're getting pretty close. We're up to the 1.6 gig, which is almost double the amount of memory. Again, we've set this priority high, and we set the buffer high. All the other virtual machines have a lower memory setting, so they'll basically be giving up memory to make sure that this one has the memory it needs. So there is dynamic memory in action. What do you guys think? All right. Excellent. Okay. So let's switch back over. This time I'll use the right keyboard and mouse. So switch back over to my deck. Let's see if my little clicker that I dropped on the floor works. It does. That's wonderful. Dynamic memory APIs. Everything you saw us just do was obviously through the UI. Obviously, everything is also available through the APIs. Over on the left, we have the things available in the UI. There are also other options that can be triggered using the API or WMI interface. It's fully documented. Our policy with Hyper-V is always to document fully all our APIs so you can basically script and automate. That's also how System Center Virtual Machine Manager basically integrates with Hyper-V. They're all available on that document right there if you care to see the API so you can trigger this through scripts. Upgrading to R2 Service Pack 1, are there any special considerations? Are there any things that you guys need to think about before you start upgrading? It is relatively simple. The first thing you really need to do is update the host. Install Service Pack 1. This will require a reboot of the host. Your virtual machines usually are set to go into a save state upon reboot. Once the host has been updated, you need to make sure that the integration services inside the virtual machines are the same version as the host. One way to do that is to have Service Pack 1 inside the virtual machines. So if your virtual machines are running Windows Server 2008 R2, you can also update those virtual machines to Service Pack 1. That will update the integration components and make sure that the virtual machines can use dynamic memory. If they're not, you can also, in the virtual machine console itself, you can basically do the insert integration components disk. Essentially, we mount an ISO, we present it inside the virtual machine, we run a setup application, and we install the latest version of the integration components. At that point, you can then turn off your virtual machine. You can then change the memory settings of your virtual machine for dynamic memory, reboot your virtual machine, and you'll be fully using dynamic memory. It's a relatively simple process. System impact, this is just as an FYI. So Hyper-V has always had the concept of reserved memory. Hyper-V, even before dynamic memory, is obviously giving its memory resources of the host into the virtual machines, but we've always had the concept of reserve for the host. We want to make sure that the host is never starved. We want to make sure that the host is always responsive. The host reserve traditionally has always been auto-calculated. We take a look to see if SLAT, second level address translation, is present inside the virtual machine. We take a look at the total amount of memory inside the host. If it's a NUMA architecture, and I'll talk about NUMA in just a minute, we also take that into factor. However, now with dynamic memory, we've made some changes to the reserve. It is possible with dynamic memory that all the virtual machines will basically be pushing right up to the reserve consistently. And so it is possible, before we made these modifications and changes, that the host would actually start to get starved of resources. We've made modification on our reserves to make sure that we always protect the parent partition, but we've also given you the option to make modifications as well if you see fit. This is more of an advanced setting. This isn't usually, again, in 9 times out of 10 or 99 times out of 100, you can just let the system do it. It will reserve enough for the host. But in some instances, it is actually useful to modify it yourself. So we've actually included a registry key that allows you to reserve static amount of memory for the parent partition. In some cases, people choose to do this if they're running other workloads on the host as well. So maybe you're running, Active Directory on the host or SQL on the host. First of all, not supported, not recommended in a production environment. Our support policy says if you're running Hyper-V in production, Hyper-V is the only thing on the host. If you need to run Active Directory, great, put it inside the virtual machine. But in some demo environments or dev environments where you're just running it and trying things out, there are some cases where people like to run other things on the host. That's just one example why you might want to go ahead and change the host reserves. We now provide you a key to do exactly that. All right, one of the last things I want to talk about is NUMA. Frankly, there's still a lot of people out there that aren't familiar with NUMA, so let me ask you by a show of hands, how many people know what NUMA is? Okay, probably about a quarter to half the audience. So NUMA is basically a different kind of computer architecture. What we see on the screen here is more of a traditional one. Here on the bottom, we obviously have our CPUs. We have our bus. We have our memory. Here we're computer. In this case, we can call this the virtualization host or Hyper-V. And of course, we have all the virtual machines on top. The virtual machines on top all go through the same bus, all use the same memory, and all have access to the same CPUs. But in some systems, very, very large systems, where we're starting to add large numbers of CPUs and large amount of memories, the bus can actually become a bottleneck. And so in a traditional NUMA architecture, what essentially we're doing is breaking the system into multiple nodes. It's kind of carving the system into multiple separate computers. So now we have node 1, and it's allocated half the CPUs. It has its own bus, and it's allocated half the memory. We have node 2, which again has the other half of the available resources. All the virtual machines sit on top. Now, by default, does Hyper-V support NUMA? Absolutely it does. By default, what we try to do is avoid what is called NUMA spanning. NUMA spanning is when you're using some resources on one NUMA node and other resources on the second NUMA node. There are significant potential performance deficiencies that you can experience by NUMA spanning. So by default, Hyper-V tries to always stay on the same NUMA node. So this virtual machine, for example, will pull memory from this node over this bus and CPU from the same node. This is good. This is what is supposed to happen. However, it can happen that if available resources aren't on the NUMA node that the virtual machine is running on, that it will span. So as you can see, this virtual machine is grabbing CPU from this NUMA node and memory from that NUMA node. That can be bad. You can see performance degradation when that happens. So again, first in default, Hyper-V always tries to get the memory from a single NUMA node. It tries to avoid NUMA spanning if possible. When it cannot, it can span NUMA nodes. You can set the preferred NUMA nodes for a virtual machine in order to get the best distribution. And also, we can basically have added the options in the Hyper-V Manager to basically disable NUMA spanning if you want to. Now, by disabling NUMA spanning, it is possible that your virtual machine consolidation will decrease. Why? Because maybe memory is available on the other NUMA node, but your virtual machine is on the first NUMA node, and you've told it don't go across nodes to get memory. So you might have available resources, but because you've disabled this option, it's not using it. So this is really a consolidation to performance benefit. We give you the option to go either way. Most systems out there, I would wager a guess that 90% of your systems out there, if not more, aren't NUMA aware anyway, so this isn't really of much consolation. It doesn't really make much effect, but regardless, we do have the option to change that. And just for fun, I'll switch over really quick back to my host. I'll just show you where the setting is. If you go into the Hyper-V settings, and this is done based on a system, it's right here, NUMA spanning. The default is to allow NUMA spanning. You simply can check that box if you want to disable NUMA spanning. That is a new setting that is in Hyper-V Manager with Service Pack 1. Okay, switching back. So again, disabling NUMA spanning, essentially, we're partitioning or we're sectioning off, not allowing virtual machines to go across the nodes. So what is the call to action? What do I want you to do? Go try it. You saw the demo today. The demo today was not intended to be an exact replica of a production environment. It was just to get an understanding and an idea of how it works. I highly encourage you to download Service Pack 1 today. It is available. It is RTM. The feedback thus far have been absolutely phenomenal, but I'd like to hear your feedback. Please start to investigate it, try it out, let us know what you think. I have a feeling you will be pleasantly surprised. So that is it. I think we are right at time. I got my little red button.